Most of the universe is made of something we cannot see. An invisible substance, a cosmic puppeteer, pulls the strings of galaxies and guides the shape of the cosmos itself. This is dark matter. For decades, scientists have followed clues about this elusive material, which makes up roughly 27% of everything yet slips through our best detectors unseen. How can something we cannot touch hold such influence over the motion of galaxies and the largest structures in existence? We will trace the path of evidence from its earliest historical hints to the modern experiments of today, revealing the unseen forces that shape our reality. By the end, you will understand why this mystery is so important to our very place in the cosmos. Why do stars on the edge of a galaxy move in unexpected ways? And what imprint does dark matter leave using light itself as its canvas? What does it mean that the universe is filled with a presence we can only sense through its immense gravitational influence? The serene spiral of a galaxy, with its brilliant core and sweeping arms, appears to be a place of orderly motion. But in the 1960s, astronomer Vera Rubin noticed something deeply unexpected about the Andromeda galaxy. She found that stars far from the galactic center were orbiting at nearly the same incredible speed as those closer in. This was not just a small anomaly, it was a fundamental shift in understanding. According to the established laws of gravity, the outermost stars should have been moving much more slowly, like the outer planets in our solar system that crawl along their orbits. The fact that they were not suggested that something profound was missing from our picture of mass. Vera Rubin's meticulous observations revealed a consistent pattern across galaxy after galaxy. The visible stars and gas simply did not provide enough gravitational pull to explain these high velocities. There had to be something else, a vast amount of unseen material, providing an extra gravitational anchor. This unseen component was not a small amount. It was the overwhelming majority of a galaxy's substance. Think of our own Milky Way. For the Sun to orbit the center at its current speed of nearly 500,000 miles per hour, the galaxy must contain far more matter than all its glittering stars and nebulous gas clouds combined. The only way to explain how stars can race along their paths without flying off into the void is if the entire visible galaxy is embedded within a gigantic, massive halo of something we cannot see. This unseen structure holds the stars in its gravitational embrace, orchestrating their motion from the shadows. What does it mean that the laws of physics, as we know them, do not fully explain the most basic behavior of galaxies? This was the first solid clue that we were missing almost the entire cosmic picture, a realization that would inspire a complete rethinking of the universe's composition. That same gravitational pull, invisible yet undeniable, does more than just steer stars. It warps the very fabric of space and time, bending the path of light itself. We can witness this in a stunning cosmic illusion, a mirage on a universal scale. Imagine the light from a brilliant, distant quasar, a beacon from the edge of the observable universe, traveling for billions of years only to have its path curved by a massive galaxy cluster in the foreground. From our vantage point, we do not see one image of that quasar, but multiple, smeared into faint, luminous arcs around the cluster. This is not a trick of the optics, it is a direct prediction of Einstein's theory of gravity, a phenomenon called gravitational lensing. The great astronomer Fritz Zwicky first proposed this idea in the 1930s, suggesting that entire galaxy clusters could act as cosmic lenses. Decades later, with powerful tools like the Hubble Space Telescope, this concept became one of our most powerful tools for mapping the invisible. The degree to which the light bends tells us precisely how much mass is in the foreground cluster, warping space-time like a heavy ball placed on a stretched rubber sheet. Time and again, the calculation reveals a surprising truth. The mass required to create these spectacular lenses is far greater, often by a factor of 5 or 10, than the mass of all the stars and gas we can see. This is the shadow signature of dark matter, revealed by its gravitational grip on light. Astronomers use two main forms of this technique. Strong lensing creates those multiple, distorted images and giant arcs, perfect for probing the dense cores of clusters. Weak lensing, a more subtle effect, causes a slight, systematic stretching of the shapes of thousands of background galaxies, allowing us to chart the vast, diffuse dark matter halos surrounding them. Perhaps the most compelling evidence from this method comes from cosmic interactions like the bullet cluster. This is a system of two galaxy clusters that have passed through one another at immense speeds. In such a dynamic event, the clouds of hot, visible gas detected by X-ray telescopes slow down and linger in the middle, like two clouds of smoke meeting. But the map of total mass created by gravitational lensing shows something astonishing. The majority of the mass, the dark matter, has continued right through the encounter and lies ahead of the gas. This shows that dark matter does not interact with itself or normal matter in the way that everyday particles do. It is truly a ghostly, collisionless substance. We are essentially seeing the dark matter separated from the visible universe by a cosmic event. If we can trace its invisible outline by watching how it bends light from distant galaxies, what does that tell us about the framework upon which the entire cosmic web is built? This hidden structure does not just influence individual galaxies, it binds the largest formations in the universe together. These faint whispers from the dawn of time offer our third compelling clue. Billions of years ago, the entire cosmos was a hot, dense sea of particles and light. As the universe expanded and cooled, light was finally set free, creating a relic glow that still permeates all of space. This is the cosmic microwave background, a snapshot of the universe in its infancy. It appears almost perfectly uniform, a blanket of microwave radiation. But when we look with exquisitely sensitive instruments like the Planck satellite, we see tiny variations, patterns of slightly warmer and cooler spots imprinted across the sky. These minute temperature differences are the seeds of everything we see today, the blueprints for galaxies and vast cosmic voids. The specific patterns in this ancient light hold a secret code, one that cosmologists have learned to decipher. The most prominent feature in this code is a series of peaks and troughs in what is called the angular power spectrum. The precise size and height of the first peak tells us the overall geometry of the universe, that it is flat. But the second peak is where the story of dark matter truly unfolds. Its characteristics reveal the delicate balance that occurred in the early plasma between gravity, which tried to pull matter together, and radiation pressure, which tried to push it apart. For the structures we see to have grown, there had to be a type of matter that was immune to this radiation pressure, a substance that could begin clumping together long before ordinary matter could. Only dark matter fits this role. Its gravitational pull provided the anchor, amplifying those tiny density variations into the gravitational wells that would eventually draw in normal matter and form the first stars and galaxies. This process is etched into the cosmos as baryon acoustic oscillations, faint, frozen rings in the distribution of galaxies that act as a standard ruler for measuring cosmic expansion. The data from the cosmic microwave background allows us to measure the universe's ingredients with stunning precision. It tells us that dark matter makes up about 27% of the cosmic density, while the ordinary matter that builds stars and planets constitutes less than 5%. Without this dominant, invisible component, the gravitational pull would have been too weak. The universe would have expanded too rapidly for any significant structures to form, leaving a cold, dark, and empty cosmos. There would be no galaxies, no stars, and no us. How is it that this ancient afterglow, a fossil from 13.8 billion years ago, provides such definitive proof for an invisible substance today? It reveals that dark matter is not a modern anomaly, but the fundamental scaffolding upon which the entire visible universe was built, a cosmic architect present from the very first moments. The blueprint for our cosmic neighborhood was drawn by an unseen hand. This invisible scaffolding guided the growth of everything we see, from the smallest dwarf galaxies to the largest structures in the universe. Without its subtle influence, the cosmos would be a formless, featureless void. How do we know this hidden framework exists? The answer lies in the grand architecture of space itself, revealed through immense computer simulations. When scientists program the laws of physics into supercomputers and model the evolution of the universe, they run a critical test. They create two versions of cosmic history, one with only the ordinary matter we see, and another that includes the gravitational pull of this unseen component. The results are unequivocal. Simulations like the famous Millennium Run show that without it, the universe expands too quickly. The feeble gravity of visible atoms cannot overcome this expansion to form any significant structures. Galaxies simply do not assemble. But when this invisible presence is added to the simulation, something remarkable happens. Its gravity provides the necessary anchor. Tiny density fluctuations in the early universe, which we see imprinted in the cosmic microwave background, are gently amplified. This unseen substance begins to gather first, forming a vast cosmic web of delicate filaments. Over billions of years, this web grows, with immense halos coalescing at the intersections of these strands. It is into these gravitational wells that ordinary matter, the gas that forms stars and planets, eventually settles. This process creates a beautiful hierarchy of structure that matches our observations perfectly. We see dwarf galaxies, which are rich with this unseen influence, orbiting larger galaxies. We see galaxies themselves grouped into clusters, and those clusters linked by faint bridges to form superclusters, the largest known structures in the universe. The Sloan Digital Sky Survey has mapped the positions of millions of galaxies, and the resulting three-dimensional map reveals this architecture in stunning detail. It shows a universe frothing with vast, empty voids hundreds of millions of light-years across, separated by thin, interconnected walls and filaments where galaxies are concentrated. This cosmic web is a perfect match for the predictions of our models. The invisible framework has gently dictated the placement of every city of stars. What would we see if our eyes could perceive this hidden structure? We would not see isolated islands of light, but a continuous, luminous web with galaxies strung along its strands like dew on a spider's silk. This profound understanding of its role as the cosmic architect brings us to the ultimate challenge. If it is everywhere, shaping everything, how do we finally catch it? Catching a ghost requires a trap of almost unimaginable sensitivity. This is the immense challenge of direct detection, the bold effort to feel the faintest whisper of a dark matter particle as it drifts through the Earth. Scientists are not building telescopes for this hunt. They are constructing the most quiet and shielded environments on the planet, often deep inside mountains or in former mine sites. The goal is to witness a single, rare interaction between a dark matter particle and the nucleus of an ordinary atom. Imagine a vast tank filled with liquid xenon, chilled to extreme temperatures. If a dark matter particle, theorized to be a type of weakly interacting massive particle or WIMP, were to gently interact with a xenon nucleus, it would produce a tiny flash of light and a minute electrical charge. Experiments like LUX Zeppelin and XENONNT are designed to be exquisitely sensitive to these twin signals, using arrays of powerful light sensors to capture the event. The entire apparatus is a masterpiece of isolation. It must be placed under a mile of rock to shield it from the constant rain of cosmic rays that would otherwise overwhelm the detector. The materials used in the detector itself are meticulously chosen for their ultra-low natural radioactivity. One researcher described the effort as listening for a single pin drop in a roaring hurricane. You have to build a room so quiet that you can finally hear that one soft sound. This painstaking work has led to one of the most tantalizing and debated stories in modern physics, the signal from the DAMA LIBRA experiment. Located deep under the Gran Sasso mountain in Italy, this experiment has reported a curious rhythmic pattern for over 2 decades. Its data shows a tiny annual rise and fall in its detection rate, which the team suggests could be caused by our solar system moving through the galactic dark matter halo. As Earth orbits the Sun, our planet's velocity relative to this halo changes, creating a wind that might be slightly stronger in June and weaker in December. This annual modulation is a predicted signature for dark matter, yet no other major experiment has been able to confirm this signal, leading to a long-standing and respectful discussion within the scientific community. Could DAMA be seeing something exotic that others are not? Or is there a more conventional explanation hidden in the complex environment? This mystery drives the field forward, pushing for ever larger and more sensitive detectors to provide a definitive answer. What would it mean for our species to finally record a direct signal from the invisible 85% of the universe's matter? It would be a discovery on par with understanding the atom, a fundamental rewriting of our place in the cosmic order. And while this direct hunt continues underground, other scientists are looking to the skies for a different kind of evidence, searching for the faint, secondary glow of dark matter transforming in the void of space. Deep underground, we listen for whispers, but high above, we search for echoes. Another powerful method for uncovering dark matter involves looking not for the particles themselves, but for the light and energy they might leave behind. This is the hunt for indirect detection. The theory suggests that when 2 dark matter particles meet, they could transform in a brilliant release of energy, creating a cascade of secondary particles that we can actually observe, such as gamma rays, neutrinos, or antimatter. We are essentially trying to detect the ghost shadow, the faint afterglow of its transformation. To do this, scientists use incredible instruments like the Fermi Gamma Ray Space Telescope, which scans the sky for high-energy gamma-ray light, and immense ground-based observatories that detect the particle showers created when gamma rays strike our atmosphere. The search focuses on places where dark matter is predicted to be most dense and its interactions most frequent. The center of our own Milky Way galaxy is a prime target, a region where the invisible halo is thought to be most concentrated. For years, astrophysicists have been analyzing a curious and persistent signal from this region known as the Galactic Center, GVXS, an unexpected surplus of gamma rays at a specific energy. As one researcher described it, it is a signal that fits the profile of what we might expect from dark matter interactions, but the case is not yet closed. The great challenge is distinguishing this potential signal from other astrophysical sources, like the collective output of numerous spinning neutron stars, known as pulsars, which can also produce gamma rays. This is why scientists also look at dwarf spheroidal galaxies. These are small, faint satellite galaxies orbiting the Milky Way that are incredibly rich in dark matter, but contain very few of the conventional stars that could create confusing astrophysical backgrounds. They are considered pristine laboratories for this kind of search. The process of transformation can occur through different channels, each producing a unique signature in the gamma-ray spectrum. By meticulously analyzing the precise energy and distribution of these gamma rays, physicists can test specific models of what dark matter particles might be. If we were to confirm that a gamma ray signal truly comes from dark matter interactions, it would be a monumental breakthrough. It would tell us not only that dark matter exists as a particle, but it would also reveal fundamental properties about its nature, its mass, and how it interacts with itself. What does it mean about the substance shaping our universe if it can, on rare occasions, reveal itself through a brilliant, self-revealing flash of light? This pursuit of indirect clues brings us to the ultimate question, a question that pushes at the very boundaries of physics itself. What, in the end, could this invisible cosmic architect actually be made of? For decades, one candidate has stood out as an elegant solution to the dark matter puzzle. It is known as a weakly interacting massive particle, or a WIMP, and its appeal lies in a remarkable cosmic coincidence often called the WIMP miracle. The theory suggests that if such particles were created in the hot, dense conditions of the Big Bang, they would have naturally frozen out as the universe expanded and cooled, leaving behind precisely the density we observe today. The miracle is that a particle with a mass hundreds or even thousands of times greater than a proton, and which interacts only through gravity and the weak nuclear force, would annihilate and decouple at just the right rate to account for that 27% of the cosmos. This is not a fine-tuned adjustment. It emerges naturally from the mathematics of particle physics. For many theorists, this was profoundly satisfying. As one physicist noted, it felt as though the universe was giving us a clear signpost. WIMP also fit beautifully into ambitious theoretical frameworks like supersymmetry, which proposes a partner particle for every known particle in the Standard Model. The lightest of these supersymmetric particles would be stable, neutral, and interact only weakly, making it a perfect WIMP candidate. This elegant connection between the largest scales of cosmology and the smallest scales of particle physics made WIMP the dominant candidate for a generation. The story of their predicted creation is a journey back to the universe's first moments. In the searing heat of the early cosmos, particles and their antiparticles were constantly colliding and transforming into energy, maintaining a state of thermal equilibrium. But as the universe expanded and cooled, the density of particles dropped. At a critical point, WIMP would have become so spread out that they could no longer find each other to annihilate. Their population effectively froze out, leaving a relic density that simply drifted through the expanding space. This process, known as thermal freeze-out, left behind a specific abundance of these particles that, according to the calculation, matches our observations of dark matter almost exactly. This powerful theoretical motivation fueled an immense global hunt. The direct detection experiments placed deep underground with their vats of liquid xenon were designed specifically to catch the faint nuclear recoil from a passing WIMP. The indirect searchers scanning the galaxy for gamma rays were looking for the telltale signature of WIMP annihilating each other in the dense halo of the Milky Way. For years, this was the primary path of investigation. Yet, despite decades of increasingly sensitive searches, a definitive WIMP signal has remained elusive. The parameter space where these particles were expected to live has been systematically narrowed, ruling out the simplest and most attractive models. The great question now hangs in the air. If WIMP are such a perfect theoretical fit, Why does the universe seem to be hiding them from our view? This persistent absence has forced physicists to broaden their imagination, to consider that the true nature of dark matter may be far stranger and more exotic than we ever anticipated. The persistent silence in the hunt for heavy WIMP has opened the door to a radically different idea. What if dark matter is not made of rare, massive particles, but is instead a universe-filling ocean of something incredibly light? This is the world of Axions and other ultralight candidates, where the fundamental nature of the invisible substance shifts from a sparse hail of bullets to a deep, coherent wave. Axions were first imagined by physicists not for cosmology, but to solve a deep puzzle in the theory of the strong nuclear force, known as the strong CP problem. This problem asks why the strong force which binds atomic nuclei seems to respect a certain symmetry that it technically should not. The Axion was an elegant solution, a hypothetical particle whose existence would naturally restore this balance. In a beautiful twist, researchers soon realized this same particle could also account for the dark matter saturating the cosmos. Unlike WIMP, which could be hundreds of times heavier than a proton, an Axion would be billions of times lighter than an electron. At such a tiny mass, these particles would be unimaginably numerous, forming not a sparse collection of discrete objects, but a continuous, oscillating field that permeates every corner of space. You would not detect a single Axion hitting a detector. You would sense the collective hum of the field itself. This leads to a completely different search strategy. Experiments like the Axion Dark Matter Experiment, or ADMX, are not placed deep underground listening for nuclear recoils. They use powerful, tunable magnetic fields and highly sensitive resonant cavities, essentially empty metal chambers, to coax this cosmic field to reveal itself. The idea is that in the presence of a strong magnetic field, an Axion could convert into a very faint microwave photon. As one researcher from the ADMX collaboration describes it, they are tuning their cavity through different frequencies, much like turning a radio dial with immense precision, listening for one specific station in a sea of static, the station that would be the signature of the Axion field. The behavior of such light dark matter is profoundly strange, because Axions are bosons, a type of particle that can occupy the same quantum state. They could theoretically form a Bose-Einstein condensate on a galactic scale. This means the entire dark matter halo of a galaxy could behave as a single, gigantic quantum object, a coherent wave function guiding the motion of stars. The contrast with the WIMP paradigm is stark. WIMP are the solitary giants, the elusive climbers we try to spot one at a time. Axions are the collective choir, a field whose power comes from its unity. This shift in perspective forces us to ask a fundamental question. Could the invisible 85% of the universe be a substance so light and so pervasive that it is less a collection of things and more a property of space itself? This line of thinking invites even more exotic possibilities, where the answer lies not in new particles, but in modifications to the most fundamental laws we think we know. Perhaps the most dramatic possibility is that dark matter is made of black holes, not the stellar giants born from collapsing stars, but ancient relics from the universe's explosive first moments. These primordial black holes would have formed when intense density fluctuations in the early cosmos caused pockets of space to collapse directly under their own gravity. This idea elegantly sidesteps the need for any new, exotic particles, relying instead on the known, powerful force of gravity alone. Cosmologists exploring this path envision a cosmos filled with these invisible gravitational anchors, ranging in mass from something as small as an asteroid to many times the mass of our Sun, all drifting unseen through the vastness of space. The evidence for this idea, however, is a puzzle of constraints and tantalizing hints. Extensive microlensing surveys, which watch for the temporary brightening of a star when a massive object passes in front of it, have largely ruled out a universe where dark matter is predominantly made of black holes in certain mass ranges. If countless asteroid-mass black holes filled our galaxy's halo, we would see frequent, characteristic flickers in the light of stars in nearby galaxies like the Magellanic Clouds. We do not see enough of these events to account for all the dark matter, yet a window remains open for other mass ranges. This is where the revolutionary observations from gravitational wave observatories like LIGO enter the story. LIGO has detected the ripples in spacetime from merging binary black holes, some of which are surprisingly heavy. The origin of these black holes is an open question. Could some of them be primordial, ancient black holes that have been orbiting each other since the beginning of time? Their existence does not prove the case for dark matter, but it keeps the possibility alive and compelling. If dark matter is indeed a sea of ancient black holes, it forces us to reimagine cosmic history. It means that the first structures to form after the Big Bang were not gentle clouds of gas, but profound knots of space-time curvature. These black holes would have been the first gravitational seeds, around which normal matter later gathered to build the galaxies we see today. How would our understanding of the universe shift if we knew its invisible backbone was woven from the fabric of spacetime itself, tied into billions of timeless knots? This candidate beautifully bridges the world of particle physics, where those initial density fluctuations are born, with the pure gravitational physics that governs the cosmos on its largest scales. The nature of this unseen cosmic substance is not uniform. It can be thought of as a fluid, and like any fluid, its temperature influences how it moves and gathers. In the cold dark matter picture, this fluid is slow-moving. Its particles are massive and travel at low speeds, which lets them come together easily from the very beginning, forming the seeds of the immense cosmic web we see today. This cold model has long been the leading idea, successfully matching the large-scale arrangement of galaxies and clusters. Yet as our simulations become more advanced, a subtle tension appears on smaller scales within the local environments of individual galaxies. The cosmos appears to be smoother than our models anticipate. As one simulations expert observed, we perform these enormous cosmic calculations and repeatedly encounter what is known as the missing satellites issue. The cold dark matter model suggests our Milky Way should be orbited by a swirling entourage of many hundreds of small dwarf galaxies, but we detect only a few dozen. Where are all the others? This puzzle has encouraged scientists to consider a warmer possibility. Warm dark matter would be made of lighter, faster-traveling particles. Imagine the difference between honey and water. Cold dark matter behaves like honey, viscous and inclined to form clumps across all scales. Warm dark matter is more like water, flowing quickly and smoothing over the tiniest wrinkles. It would limit the emergence of those smallest dwarf galaxies, offering a possible answer to the missing satellites mystery. A candidate for this warmer substance might be something like a sterile neutrino, a hypothetical, heavier relative of the standard neutrino that interacts only through gravity. How do we measure this cosmic temperature? One powerful method examines the ancient light from far-off quasars. As this light journeys for billions of years to reach us, it passes through the scattered clouds of hydrogen gas that outline the cosmic web. Certain wavelengths in the quasar's light are absorbed by this hydrogen, producing a forest of absorption lines in its spectrum. This Lyman alpha forest serves as a preserved imprint of structure in the early universe. A cold dark matter cosmos would reveal a very dense, intricately detailed forest, filled with narrow absorption lines from innumerable small gas concentrations. A warm dark matter cosmos would yield a more open, smoother forest, since the faster-moving particles would have erased those smallest features. Current data tends to support the cold model, though the findings are not yet definitive. Another important test exists right in our own galactic neighborhood with the ultra-faint dwarf galaxies. These are the dimmest, most dark matter-rich objects we have identified. If cold dark matter is accurate, there should be a huge population of even fainter, still unseen dwarfs circling our galaxy. If warm dark matter is correct, we might have already located the majority of them. The ongoing, careful survey of these galactic phantoms is more than a simple count. It is a direct way to measure the fundamental nature of the cosmos's unseen architect. Do these smallest and most pristine galaxies hold the final clue to telling a cold universe from a warm one? The answer will decide whether dark matter is an ocean of heavy, isolated giants or a swift current of lighter, more elusive particles. The invisible cosmic architecture seems to falter at its very heart. Deep within the tranquil centers of galaxies, a profound disagreement emerges between our most sophisticated simulations and the reality we observe. This is the Core-Cusp Problem, a stubborn puzzle that challenges the very foundation of the cold dark matter model. When cosmologists run simulations with only dark matter, a clear pattern emerges. The gravitational pull should create an intensely dense central peak, a sharp cusp of invisible material. The density should rise dramatically as you approach the galactic core. Yet when astronomers train their telescopes on real dwarf spheroidal galaxies and faint, low-surface brightness galaxies, they find something entirely different. Instead of a steep peak, many reveal a constant density core, a gentle plateau of dark matter in their central regions. One astronomer studying these faint galaxies noted, "The data consistently points to a smoother distribution than our most basic models allow." It is as if we predicted a towering, jagged mountain but found a softly rounded hill. The question is, why? One promising line of investigation points to the role of ordinary matter, the baryonic physics we often overlook. While dark matter provides the gravitational backbone, the normal stuff of stars and gas is not entirely passive. In the early lives of galaxies, immense cycles of star birth and death can unleash tremendous energy. Supernova explosions can act like cosmic winds, pushing gas and even the invisible dark matter out from the center. This constant churning, known as stellar feedback, could be the sculptor that softens the sharp central cusp into a smooth, flat core. Think of it like stirring a cup of tea with a lump of honey at the bottom. The honey represents the dark matter cusp. The vigorous motion of the spoon, representing the supernova feedback, gradually mixes and smooths the honey throughout the cup, creating a more uniform distribution. This idea has gained traction as simulations have grown more complex, incorporating not just dark matter, but also the dynamic effects of stars and gas. The results are compelling, showing that baryonic processes can indeed flatten those dense central peaks. Yet another proposal is even more radical. What if dark matter is not entirely collisionless? The self-interacting dark matter model suggests that dark matter particles might occasionally bounce off one another, a subtle repulsion that would smooth out the central density. In this scenario, the particles in the crowded galactic center would scatter, transferring energy and migrating outward to create a constant density core. This is a small but significant departure from the standard model, where dark matter particles are ghosts that pass through each other without a trace. The cosmic picture was further complicated by the discovery of galaxies like NGC 1052 DF2. This strange, diffuse galaxy appears to have almost no dark matter at all. Its stars move at speeds that can be entirely accounted for by the visible mass alone. This was a stunning finding. If a theory can explain why some galaxies have too much dark matter in their cores, it must also explain why others seem to have none. The existence of such galaxies suggests that the connection between dark matter and visible matter is far more complex and decoupled than we imagined. Are we missing a fundamental rule about how dark matter gathers, or how it interacts with the normal universe? This persistent mystery at the heart of galaxies forces a profound question. Could the solution lie not in finding a new particle, but in rewriting our understanding of the force that binds the cosmos together? Perhaps the most radical answer to the dark matter puzzle is that we have been asking the wrong question entirely. What if the invisible substance is not a substance at all, but a sign that our grasp of gravity itself is flawed on the vast, dimly lit stages of galaxies? This is the bold proposal of modified Newtonian dynamics, or MUND, first introduced by physicist Mordechai Milgrom in the early 1980s. Milgrom suggested that instead of invoking an entire universe of unseen matter, we might simply need to adjust Newton's laws for the extremely weak gravitational accelerations found in the outer reaches of galaxies. His idea was elegantly simple, that gravity does not fade with the square of the distance as we have long believed, but transitions to a different, stronger behavior when its pull becomes incredibly faint. At these low accelerations, a new constant of nature would take over, giving gravity an extra boost. With just this single adjustment, MUND achieves something remarkable. It can precisely predict the flat rotation curves of spiral galaxies without a single gram of dark matter. The observed speed of stars perfectly matches the modified gravity calculation, a success that has persisted across hundreds of galaxies. Proponents of MUND see this as a powerful argument for simplicity. Why invent an entire invisible cosmos, they argue, when a small tweak to a known law can so elegantly explain the data right in front of us? Yet for every success, MUND faces a profound challenge. Its most significant difficulty arises in the aftermath of cosmic collisions, like the Bullet Cluster. In that system, the gravitational lensing map shows the mass clearly separated from the visible gas, a direct signature of some form of matter that does not interact with light. MUND, which modifies the force of gravity based on the distribution of visible matter alone, struggles to account for this separation. It requires adding some form of unseen, hot matter to make its predictions work, which to critics begins to look suspiciously like a form of dark matter. The theory also has a harder time explaining the precise patterns in the cosmic microwave background and the formation of the large-scale cosmic web, phenomena that the standard dark matter model handles with impressive accuracy. The debate between these two worldviews is a fascinating division in modern cosmology. One side argues for the existence of a vast, unseen component to the universe, a hidden architecture we are only beginning to map. The other contends for a fundamental revision of one of physics' most cherished laws, a change that would ripple through our entire understanding of the cosmos. This forces a deeply philosophical question. Is it more parsimonious to fill the universe with a ghostly substance we cannot see, or to rewrite the laws of physics that have guided our exploration for centuries? The choice is not just about data, but about how we fundamentally interpret the cosmos and our place within it. Every great city in the cosmos was built upon invisible foundations. The majestic spiral of a galaxy, with its brilliant stellar disk and glowing core, is not the primary structure, but rather the luminous decoration upon a far more massive, unseen frame. This dark matter halo is the true birthplace of a galaxy, the gravitational cradle that dictates its entire life story, from its fiery infancy to its quiet, mature age. The size of a galaxy, its shape, and the very rhythm of its star formation are all orchestrated by the properties of this invisible host. Cosmological simulations like Illustris TNG bring this cosmic choreography to life, modeling not just the dark matter scaffolding but also the complex physics of the ordinary matter, the gas and stars that evolves within it. These virtual universes reveal a profound and elegant hierarchy. A small, low-mass dark matter halo will typically host a dwarf irregular galaxy, a turbulent, gas-rich system where star formation sputters along in fits and starts. A massive, sprawling halo, on the other hand, becomes the anchor for a giant elliptical galaxy, a vast sphere of ancient red stars where star formation has long since ceased. The Milky Way itself resides within a halo of about 1 trillion solar masses, a size that perfectly suits its grand spiral design. This connection between halo mass and galaxy type is one of the most robust findings in modern astrophysics. How does this structure build over time? The process is one of relentless cosmic assembly. A large galaxy like our own did not form in isolation. It grew through a history of mergers and acquisitions, steadily incorporating smaller dark matter halos and their embryonic galaxies over billions of years. The stellar streams and globular clusters we see orbiting the Milky Way are the preserved evidence of this ancient assembly process, the lasting imprints of smaller galactic building blocks. Yet the story is not one of dark matter acting alone. Within its potent gravitational grip, a dramatic feedback loop unfolds. As stars are born, the most massive ones live short, brilliant lives and explode as supernova. These events release tremendous energy into the surrounding gas, heating it and driving powerful winds that can blow the raw material for future stars right out of the galaxy. On an even grander scale, supermassive black holes at the centers of galaxies can become active galactic nuclei, pouring out intense radiation that also serves to slow star formation. This feedback is the regulatory mechanism that prevents galaxies from turning all their gas into stars too quickly. It is a delicate balancing act where the dark matter halo provides the gravitational potential well, a deep bowl that tries to hold onto the gas, while the stellar and black hole feedback acts like a series of powerful events trying to empty that bowl. The entire life cycle of a galaxy, its periods of frantic star birth and its eventual quietude, is governed by this push and pull within its dark foundation. Could a galaxy like the Milky Way, with its ordered spiral arms and diverse stellar populations, ever have formed without this deep, invisible gravitational anchor to gather and shape the primordial gas? The clear answer from simulations is no. Dark matter is not merely an add-on to our universe, it is the creative force, the cosmic architect that made the stellar cities we call home possible, weaving them into the largest structure of all. This cosmic architecture extends far beyond any single galaxy, weaving the largest known structure in existence. The universe is not a random scattering of stars and galaxies, but a vast, interconnected network often called the cosmic web. This magnificent pattern, with its dense clusters, long, delicate filaments, and immense, empty voids, is the ultimate expression of dark matter's gravitational influence. It is the framework upon which the visible universe is arranged. We can see the outline of this web through massive redshift surveys, projects that have meticulously mapped the three-dimensional positions of millions of galaxies. These maps reveal a stunning truth. Galaxies are not scattered randomly. They are concentrated along faint, interconnected threads, with huge clusters forming at the places where these threads intersect, like glittering cities at the crossroads of unseen pathways. Cosmologists note that this entire structure grew from the tiniest of seeds, those minute temperature variations in the cosmic microwave background, the blueprint of the early universe, were amplified over billions of years by the steady pull of gravity. Dark matter, being immune to the pressure of radiation, was the first component to begin gathering together. As one researcher explains, dark matter's gravitational instability provided the initial foothold, the subtle concentrations that would slowly, over cosmic time, draw in more and more matter. The process of structure formation follows a clear sequence. First, dark matter collapses to form halos, the gravitational wells we discussed earlier. Then, ordinary gas composed of baryons falls into these wells. As the gas compresses and cools, it eventually ignites into the first stars, lighting up the galaxies that mark the nodes and strands of the web. To map this unseen framework, astronomers use powerful techniques. Weak gravitational lensing allows them to chart the distribution of mass, including the dark matter, by measuring how its gravity subtly distorts the shapes of millions of background galaxies. Another method, studying galaxy correlation functions, analyzes the statistical clustering of galaxies to infer the underlying dark matter structure they trace. A classic example of a dense node in this web is the Coma cluster. This is a massive collection of thousands of galaxies, but the visible galaxies are just the surface layer. The cluster is embedded within a far larger halo of dark matter, and it is connected by faint filamentary bridges to other clusters and groups, part of the larger cosmic superstructure. How does this hidden framework guide the entire organization of the universe we see? It dictates the flow of galaxies, the location of the great voids, and the very pathways along which cosmic evolution unfolds. This grand, unseen architecture does not just shape space, it also holds a deep influence over time, guiding the ultimate future of the cosmos itself. The invisible cosmic web weaves the structure of space, but its gravity also holds the key to time itself. The ultimate fate of our universe, whether it expands forever or eventually draws back together, is shaped by a delicate tug of war between two unseen giants. On one side is the relentless push of dark energy, and on the other is the steady, anchoring pull of dark matter. This cosmic competition is described by a set of equations known as the Friedmann equations, which act as the universe's vital signs, tracking its expansion rate and energy content over billions of years. The density of dark matter is a critical parameter in these equations, a value that tells us just how much gravitational influence exists to balance the outward thrust of dark energy. As one cosmologist noted, we are living in a special era where these two titans are nearly in balance, but the scales are tipping. The evidence for this cosmic interplay comes from two powerful and independent lines of observation. The first is the study of distant supernovae. By observing how the light from these stellar explosions dims and stretches over vast distances, astronomers can map the expansion history of the universe. These surveys revealed the surprising acceleration of cosmic expansion, the signature of dark energy, but they also precisely measured how the expansion was slower in the past, when the universe was denser and the gravitational influence of dark matter was more dominant. The second line of evidence comes from the frozen sound waves of the early universe, the baryon acoustic oscillations. These subtle, repeating patterns in the distribution of galaxies act as a standard ruler. By measuring the apparent size of these patterns at different cosmic epochs, scientists can trace how the expansion rate has changed, further clarifying the roles of both dark matter and dark energy. The data from the Planck satellite provides the most precise numbers for this cosmic budget. It tells us that dark matter contributes about 27% of the total energy density of the cosmos, while dark energy makes up a remarkable 68%. Ordinary matter, everything we see and are made of, accounts for less than 5%. This brings us to the concept of critical density. the precise amount of matter and energy needed to just barely halt the universe's expansion after an infinite amount of time. Our universe appears to be at or very near this critical value, a state known as flatness. Without dark matter's significant gravitational contribution, the total density would be far too low. The universe would have expanded so rapidly from the beginning that gravity could never have gathered the primordial gas into the first galaxies. There would be no stars, no planets, and no one to ponder the cosmos. How is it that an invisible substance, which we can only sense through its gravity, holds such sway over the ultimate destiny of everything? The answer lies in the deepening mystery of its relationship with the even more enigmatic force of dark energy, a partnership that writes the final chapter for all of creation. This cosmic tug-of-war between the pull of gravity and the push of expansion defines the entire life story of our universe. Dark matter, with its steady gravitational hand, works tirelessly to pull matter together, weaving the cosmic web. Dark energy, in stark contrast, is the mysterious force driving the accelerated expansion of space itself, pushing the cosmic architecture apart. Today, dark energy is the dominant component, constituting about 68% of the cosmos, with dark matter a crucial 27%. Their dynamic interaction over billions of years has sculpted the universe we observe. As one cosmologist framed it, we are living in a curiously special time, a cosmic moment where the densities of these two titans are remarkably comparable. This is known as the coincidence problem, and it invites a profound question: why now? Why, after 13.8 billion years, do we find ourselves in an era where these two fundamental but opposing influences are of the same order of magnitude? The answer lies in tracing their influence back through cosmic time. In the early universe, radiation was the first dominant force, but as the cosmos expanded and cooled, dark matter quickly took over. For billions of years during the matter-dominated epoch, dark matter's gravity provided the anchor that allowed galaxies and clusters to form. Its persistent pull amplified the tiny seeds from the Big Bang into the vast structures we see today. Then, roughly 5 billion years ago, a cosmic threshold was crossed. The universe had expanded so much that the density of matter dropped low enough for dark energy, which does not dilute with expansion, to become the dominant component. This is when the expansion of the universe began to accelerate, a discovery that earned the Nobel Prize in 2011. To understand the nature of dark energy, scientists probe its equation of state, a single number that describes the relationship between its pressure and density. For a simple cosmological constant, as proposed by Einstein, this value is exactly -1. Precision measurements from supernova, the cosmic microwave background, and baryon acoustic oscillations all work to measure this number, testing whether dark energy is truly constant or something more dynamic that evolves over time. The timeline of the universe reveals this grand handover of power, from the initial burst of inflation to the early plasma, to the long era where matter ruled and structures grew, and finally to our current epoch, where dark energy dictates the future. This profound interplay invites us to explore a fundamental mystery. Are dark matter and dark energy two entirely separate phenomena, one pulling and the other pushing? Or could they be different manifestations of a single, unified underlying substance? Some theoretical models suggest they might be linked through a cosmic field that evolves, their influences changing as the universe ages. This idea encourages us to consider a reality where the visible world is just a fleeting pattern on the surface of a deeper, darker ocean whose true nature we are only beginning to sense. Perhaps these two cosmic titans are not separate forces at all, but different faces of a single, deeper entity. This is the provocative hypothesis of a unified dark sector, where dark matter and dark energy are intertwined manifestations of one underlying substance, a cosmic field that evolves and changes its behavior over the lifetime of the universe. For theorists seeking a more elegant cosmology, this is a compelling path. The standard lambda cold dark matter model treats dark energy as a constant and dark matter as a collisionless fluid, a framework that works remarkably well but leaves profound questions unanswered. Why do these two dark components have densities that are, coincidentally, of the same order of magnitude in our current epoch? Could this be a clue that they share a common origin? One leading candidate for this unified substance is a dynamic scalar field known as quintessence. Unlike a static cosmological constant, quintessence is a field that can slowly roll down its potential energy slope, its properties changing over billions of years. In the early, dense universe, this field could have clustered under gravity, behaving just like cold, dark matter and providing the scaffolding for galaxies. Then, as the universe expanded and thinned out, the field's energy density could have come to dominate, creating the repulsive force we call dark energy. This single entity would thus wear two masks, first as the architect of structure and then as the driver of acceleration. An even more exotic proposal is Chaplygin gas, a theoretical fluid with a very unusual property. At high densities like those in the early universe, it exerts zero pressure and clumps together under gravity, mimicking dark matter. But as the universe expands and its density drops, its pressure becomes negative, causing it to accelerate the expansion, just like dark energy. It is a chameleonic substance that transforms its fundamental nature based on the environment. Think of a material that acts like solid rock when it is packed tightly together, but then morphs into an expansive, pushing foam when it is allowed to spread out. This single fluid could, in principle, account for the entire dark sector. The motivation for these models is a deep desire for simplicity and unity in our physical theories. As one theorist explained, the standard model requires us to put in two completely independent and mysterious components to make the cosmology work. A unified model would be far more economical, deriving the behavior of both from a single set of equations. The challenge, however, is formidable. These models predict an evolving equation of state for dark energy, a value that changes over time rather than remaining fixed at -1. They also often include interactions between this unified substance and ordinary matter, a subtle coupling that could leave imprints on the growth of cosmic structure. Testing these ideas pushes our observational capabilities to their limits. Future missions like the Euclid Space Telescope and the Vera C. Rubin Observatory will map the cosmos with unprecedented precision. They will measure the history of cosmic expansion and the growth of large-scale structure, searching for tiny deviations from the predictions of the standard model. If the dark sector is truly unified, its signature might be found in a specific telltale pattern of how quickly clusters of galaxies formed at different times in cosmic history. The data will act as a referee, judging whether the universe requires two independent dark unknowns, or if a single, elegant theory can explain both the clustering that builds galaxies and the acceleration that dictates our ultimate fate. While our deepest detectors listen in silence and our telescopes scan for faint glows, another path to discovery brings matter together with incredible energy. Particle colliders like the Large Hadron Collider offer a completely different approach, one that seeks not to find dark matter in the wild, but to produce it right here in the laboratory. As one physicist from the CERN laboratory explains, we are trying to summon the invisible into existence. By recreating the intense energies present in the early universe, we can search for particles and forces that have been hidden from us since the dawn of time. This method of collider searches forms the third pillar of the hunt, a powerful complement to the direct and indirect techniques. The strategy depends on a simple but profound signature: missing energy. When two protons are accelerated to nearly the speed of light and made to collide, their energy is transformed into a shower of new particles that fly into the surrounding detectors. The total energy and momentum of everything going into that collision must, according to the law of conservation, equal the total energy and momentum of everything coming out. If we see an imbalance, if there is momentum that simply seems to vanish, it could be the telltale sign of dark matter particles being created and then flying straight through the detector without leaving a trace, carrying that missing energy away with them. The giant detectors that ring the collider, ATLAS and CMS, are essentially enormous, three-dimensional digital cameras that record the outcomes of these high-energy events. They are meticulously calibrated to measure the energy and path of every known particle that emerges. Scientists then add up all these vectors, and sometimes they find that the sums do not quite match. It is as if you were to witness a car crash where the total wreckage weighs less than the original cars, suggesting that an unseen passenger has simply walked away from the scene. Researchers have developed several clever channels to spot this missing energy. One of the most studied is the monojet event. In this scenario, a dark matter particle pair is produced alongside a single, high-energy jet of ordinary particles, like a quark or a gluon. The jet recoils against the invisible dark matter, providing a sharp kick of observable energy that signals the presence of the unseen particles. Another promising channel is vector boson fusion, where the collision produces a dark matter pair along with two quarks that emit force-carrying particles, leaving a signature of two jets in the detector with a large gap of missing energy between them. Each of these event topographies is a distinct footprint that could belong to dark matter. The hope is that with the next high-luminosity upgrade to the LHC, or with a future, even more powerful machine like the proposed Future Circular Collider, we will cross an energy threshold that finally allows these particles to be produced in abundance. What would it mean for humanity if we were to create dark matter in a lab before we ever definitively detected it in the depths of space? It would be a triumph of pure prediction and engineering, revealing the properties of this cosmic substance through the controlled conditions of an experiment. This quest in our largest machines is intrinsically linked to the surveys of our largest telescopes, together searching for the same architect in the realms of the very small and the very large. A new generation of cosmic cartographers is preparing to map the invisible. The Vera C. Rubin Observatory, with its immense 3.2 gigapixel camera, will begin the legacy survey of space and time, scanning the entire southern sky every few nights for a full decade. It will not just take pictures, it will create a motion picture of the cosmos, tracking billions of galaxies. This staggering volume of data is the key to a deeper understanding. As one project scientist for the Euclid mission explains, we are moving from studying individual galaxies to understanding the statistical properties of the entire population. This shift allows us to see the subtle patterns imprinted by dark matter with a clarity we have never had before. The primary tool for this mapping is weak gravitational lensing. By measuring the minute, systematic distortions in the shapes of billions of distant galaxies, astronomers can chart the distribution of all the mass in the foreground, the vast dark matter scaffolding of the cosmic web. The statistical power of this approach is immense. With a sample size of billions, even the most subtle distortions become a clear signal, allowing us to trace the dark matter halos around galaxies and clusters with unprecedented precision. This data will be combined with measurements of galaxy clustering from projects like the Dark Energy Spectroscopic Instrument, or DASI, which is creating a three-dimensional map of millions of galaxies. By analyzing how galaxies cluster together at different cosmic epochs, scientists can measure how the dark matter structures have grown over time, testing the fundamental predictions of our cosmological models. The Nancy Grace Roman Space Telescope will complement this by peering into the early universe, using its powerful infrared vision to find the most distant galaxies whose light has been stretched by cosmic expansion. By observing these high redshift objects, we can study the properties of dark matter when the first structures were only just beginning to form. Each of these observatories has a specific dark science case. Euclid is designed to measure the geometry of the dark universe with extreme precision. DASI is tracking the expansion history through baryon acoustic oscillations. The Roman Space Telescope will probe the nature of dark energy and dark matter by looking back to when dark energy first began to influence the cosmos. Together, they form a coordinated effort to understand the unknown. Their combined observations have the potential to resolve long-standing puzzles like the Core-Cusp and missing satellites problems. They could reveal whether dark matter is cold, warm, or something else entirely by precisely measuring the abundance of the smallest, faintest galaxies in the early universe. Or they might find something completely unexpected, an anomaly in the data that challenges our current models and forces a radical new direction in physics. What hidden facets of the invisible universe will these new eyes reveal when they turn their gaze to the deepest sky? This vast observational effort to understand dark matter's role in the cosmos inevitably leads us to a practical question. Could this mysterious substance which has shaped the universe since its birth one day shape the technology of our own future? This invisible substance may one day transform our own world. While dark matter seems distant, the quest to understand it could spark technological revolutions we can barely foresee. History is filled with examples where fundamental research into the deepest mysteries of the universe has yielded astonishingly practical applications. The scientists who first studied quantum mechanics, for instance, were exploring a strange and abstract theory, with no idea it would one day lead to the transistors powering every computer and smartphone. Similarly, our pursuit of the invisible cosmos could illuminate new paths for innovation. Innovators point out that the extreme sensitivity required to detect dark matter pushes the boundaries of measurement science. The cryogenic systems, ultra-pure materials, and incredibly low-noise sensors developed for experiments like LUX Zeppelin are masterclasses in precision engineering. These technologies could spin off into next-generation medical imaging devices, allowing doctors to detect the faintest biological signals for earlier disease diagnosis, or create highly sensitive scanners that can peer inside materials without causing damage. The challenge of spotting a single photon from a rare particle interaction drives progress in photodetection, a field that already connects astronomy to our daily lives. The Charge-Coupled Device, or CCD, was invented for astronomy to capture faint starlight, and it went on to become the heart of digital cameras, reshaping modern communication. Another frontier lies in quantum devices. Some proposed dark matter detectors rely on manipulating quantum states at macroscopic scales, a technology that could accelerate our development of quantum computers and ultra-secure quantum communication networks. Furthermore, the theoretical models developed to explain dark matter's behavior, such as its wave-like nature on galactic scales, could offer surprising analogies for understanding complex systems in condensed matter physics, potentially guiding us to new materials with extraordinary properties. Could the same principles that govern a galaxy-wide quantum condensate inspire a new class of superconductors? The potential is as vast as the dark matter halos themselves. What untapped potential for our own future lies hidden within the cosmos's most abundant yet elusive ingredient? This forward-looking perspective on technology inevitably draws our gaze from the practical to the profound, to the very meaning of our existence in a universe dominated by the unseen. Our entire understanding of reality rests upon what we can see and touch, yet the cosmos reveals that genuine substance may lie in the invisible. This brings us to a profound philosophical divide that has quietly shaped modern physics. On one side is scientific realism, the view that our best scientific theories describe entities that truly exist in the world, even if we cannot directly observe them. For a realist, dark matter is as real as the chair you are sitting on, its existence confirmed by the overwhelming consistency of its gravitational effects across the universe. The opposing view, instrumentalism, argues that scientific theories are merely useful tools for predicting observations, not necessarily literal descriptions of reality. From this perspective, dark matter is an incredibly successful calculating device, a placeholder in our equations that accurately predicts galactic rotations and gravitational lensing without us needing to commit to its ultimate physical reality. The physicist Arthur Eddington once noted that we have found a strange footprint on the shores of the unknown, and we have devised profound theories to explain its origin. What we must remember is that the footprint itself is the primary evidence. This tension is not new. Throughout history, science has inferred the existence of entities long before they could be seen. Atoms were once a philosophical concept used to explain chemical reactions, their reality debated for centuries until technology finally made them visible. Black holes were mathematical solutions to Einstein's equations for decades before we captured their shadowy silhouette. The planet Neptune was discovered not by a telescope sweeping the sky, but by pencil and paper when astronomers calculated that something massive must be perturbing the orbit of Uranus. We searched for the source of that gravitational tug and found a new world. Dark matter is our modern Neptune, inferred from the motion of galaxies on a cosmic scale. Its evidence is not a single observation but a converging pattern of clues, from galaxy rotation curves to the cosmic microwave background, that all point to the same conclusion using entirely different lines of reasoning. This very success raises a deep question. Does the fact that a theory works so perfectly make it true? History cautions us that even the most successful paradigms can be overturned. The geocentric model of the universe, with its complex cycles and epicycles, predicted planetary positions with remarkable accuracy for over 1,000 years. It was a useful instrument, but it was not a true picture of reality. Could our dark matter model, for all its predictive power, be a similar stepping stone to a deeper understanding, perhaps one involving modified gravity or a more exotic unified field? The question is not whether the effects are real. The bending of light and the swift orbits of stars are undeniable. The mystery is what causes them. Are we mapping a real, unseen cosmos, or are we reading a shadow play, a narrative written by the limits of our current physics? How does our definition of what is real evolve when the majority of the universe forever eludes our direct gaze? This cosmic mystery is not just for physicists in deep laboratories. It is a story for every curious mind. How do we explain the universe's invisible 85% to a child? Educators are finding brilliant ways to bring this abstract concept down to earth, using dark matter as a thrilling gateway into science, technology, engineering, and mathematics. A planetarium director shared her approach, saying, "We do not start with complex equations, we start with wonder. We show a beautiful spiral galaxy and ask the simple question, why does it spin so fast without flying apart?" That moment of shared curiosity is where the learning begins. To make the idea of invisible mass tangible, teachers use clever analogies. One popular demonstration involves a sealed box with a heavy, hidden object inside. Students cannot see what is in the box, but by carefully observing how it affects a rolling marble, they can infer the object's presence and even estimate its location. This is a direct parallel to how astronomers deduce dark matter by watching its gravitational pull on stars. In classrooms, students use simple simulations to model galaxy rotation curves, inputting different amounts of unseen mass to see how it changes the velocity of virtual stars. These hands-on activities transform an abstract principle into a personal discovery. Science museums and planetariums are crucial partners in this effort. Interactive exhibits might use a fabric sheet and weighted balls to demonstrate gravitational lensing, showing visitors how an unseen mass warps the path of a rolling marble, just as dark matter bends light from distant galaxies. The key messages in these public engagements focus on three pillars: the clear evidence for dark matter, the creative methods we use to hunt for it, and the thrilling open questions that remain. Perhaps the most powerful tool is direct involvement. Online citizen science projects like Galaxy Zoo invite volunteers worldwide to help classify the shapes of millions of galaxies. This massive human effort is invaluable for identifying the distorted, lensed galaxies that map the invisible dark matter web. One outreach coordinator noted, when a volunteer spots a giant arc in a galaxy image, they are not just clicking a button, they are participating in real cosmology. They are helping to chart the unseen architecture of our universe. How do we foster a lasting curiosity about the unseen in the next generation? We do it by showing that the greatest mysteries are not meant to be solved by a select few, but are open invitations for everyone to look up and wonder. This educational mission ensures that the story of dark matter transcends textbooks, becoming a vibrant part of our culture that inspires the architects and explorers of tomorrow. The invisible substance shaping our cosmos has also begun to shape our stories. Dark matter has firmly entered the realm of popular culture, transforming from an abstract scientific concept into a powerful symbol of the unknown. It appears in blockbuster films and best-selling novels, often depicted as a mysterious energy source, a gateway to other dimensions, or a tool of great potential. The television series Dark Matter and the novel of the same name by Blake Crouch use it as a central plot device, exploring themes of identity and reality through its elusive nature. A cultural observer might note that dark matter serves as the perfect modern metaphor, representing the vast, unseen forces that influence our lives in ways we can only partially comprehend. It taps into a deep human fascination with the invisible, the things that are present and powerful yet just beyond our perception. In many science fiction narratives, dark matter becomes a tool for immense possibility. A common trope portrays it as an energy source that could fuel starships or reshape worlds, a narrative that emphasizes its potential and mystery. Another frequent portrayal is that of a cosmic gateway, a substance that can be manipulated to create pathways or access parallel universes, as seen in stories where characters traverse the cosmos by harnessing its properties. These creative liberties stand in stark contrast to the scientific understanding of dark matter as a gravitationally interacting substance that does not emit, absorb, or reflect light. While thrilling, these depictions often prioritize drama over accuracy. The film Interstellar, for instance, masterfully incorporated real concepts of general relativity and higher dimensional physics, even while fictionalizing the nature of the tesseract inside a black hole. Its commitment to consulting with physicists like Kip Thorne gave its cosmic phenomena a veneer of credibility, even as it took creative leaps. This raises an important question for our media-saturated age. Does this kind of storytelling help the public grasp complex science, or does it ultimately create more confusion by blending fact with fantasy? When a viewer learns that dark matter is real from a documentary, but then sees it used as a narrative device in a movie, which version sticks in the mind? The cultural conversation around this invisible cosmic component is not just about entertainment. It is about how we collectively make sense of profound discoveries. This cultural footprint inevitably guides us toward the deeper responsibilities that come with such knowledge, prompting a necessary look at the ethical landscape of this profound research. The pursuit of the cosmos's deepest secrets is not without its weight on Earth. When we direct immense resources and intellect toward understanding an invisible universe, we must also consider our responsibilities to the visible world we inhabit. Ethicists who study the impact of big science point to a fundamental question: how do we balance our drive for cosmic knowledge with the pressing needs of our own planet? The construction of a single major observatory or a deep underground laboratory represents an investment of billions of dollars, a sum that could alternatively fund countless earthly initiatives in medicine, education, or sustainability. This is not a simple either-or choice, but a necessary tension that guides responsible stewardship. The value of fundamental research often lies in its unpredictable long-term benefits, from the technological spin-offs that revolutionize medicine to the profound cultural shift that comes from understanding our place in the cosmos. The challenge is to navigate this path with intentionality, ensuring that our reach for the stars is grounded in ethical consideration. A critical part of this is fostering genuine international collaboration. Projects like the Large Hadron Collider and the upcoming Square Kilometre Array Telescope are not owned by any single nation, but are shared endeavors involving dozens of countries. This model pools global expertise and shares the financial burden, but more importantly, it frames cosmic discovery as a shared human inheritance. The Square Kilometre Array, for instance, is being built across remote sites in South Africa and Australia. From its inception, the project engaged in extensive agreements with local communities, prioritizing local employment, investing in regional infrastructure, and respecting indigenous cultural heritage and knowledge of the land upon which the telescopes are built. This approach transforms a scientific facility into a partnership, ensuring that the host communities are not merely adjacent to discovery, but are active participants and beneficiaries. Within the research teams themselves, the ethical imperative extends to inclusivity. The questions we ask of the universe are shaped by the people who ask them. By building more diverse and inclusive teams in astrophysics, we incorporate a wider range of perspectives and experiences, which in turn leads to more creative problem-solving and a more robust, complete science. This includes a commitment to open data, where the vast information collected by these magnificent machines is made accessible to researchers and citizen scientists around the globe, breaking down barriers to participation. Even the environmental footprint of these facilities is part of the equation. The immense computing power required to simulate the cosmos or process telescope data consumes significant energy, pushing the scientific community to lead in the adoption of green computing and renewable energy sources for their operations. The underlying framework for all this is responsible innovation, a practice that asks scientists and funding agencies to consider the broader implications of their work from the very beginning. It is a commitment to ensuring that the quest to understand dark matter does not happen in an ethical vacuum, but is woven into a larger tapestry of global well-being and shared human progress. How do we ensure that the light of cosmic understanding illuminates a path that benefits all of humanity, and not just a privileged few? This reflection on our collective responsibility brings the vast cosmic mystery down to a deeply personal scale, inviting us to ask what this invisible substance means for our own existence. Carl Sagan's beautiful declaration that we are made of star stuff speaks to our tangible connection to the cosmos. Yet this luminous material accounts for less than 5% of the universe. What, then, is our relationship to the dark matter that is more than 5 times as abundant? We are not made of this invisible substance, but we are here because of it. Its gravitational architecture created the stellar nurseries where stars could form, and the galactic neighborhoods stable enough for solar systems like our own to emerge. A cosmologist might frame this through the lens of the anthropic principle, the idea that the universe's fundamental constants appear finely tuned to allow for life. In this view, the specific density and properties of dark matter are not an accident. If dark matter were significantly more or less abundant, or if it interacted more strongly, the cosmic outcome would have been radically different. The gravitational pull of dark matter was the essential anchor that slowed the expansion of the universe just enough for gravity to amplify tiny density fluctuations into the first galaxies. Without this process, the universe would have expanded too rapidly, remaining a thin, dark soup of hydrogen and helium. There would have been no galaxies, no stars, no heavy elements, and no planets. A biologist studying the conditions for life would note that while dark matter does not participate in the chemical reactions of biology, it is the unseen creator of the stage upon which biology can unfold. It guided the formation of the Milky Way, a galaxy with a quiet suburban region where our sun could form in relative isolation, shielded from the intense gravitational disruptions common in denser galactic clusters. This stability over billions of years was a prerequisite for the slow, gradual evolution of life on Earth. Speculative ideas have occasionally emerged, suggesting that dark matter particles could have some subtle, direct effect on biological processes. Perhaps some have wondered, a rare interaction could influence genetic mutation rates or even play a role in consciousness. It is a fascinating thought experiment, but it is crucial to state clearly that there is absolutely no scientific evidence for such effects. Dark matter's influence is overwhelmingly and perhaps exclusively gravitational. We are, in a very real sense, bathed in this unseen ocean. Billions of dark matter particles are streaming through your body at this very moment as you watch this, passing through you and the entire Earth as if they were not there. They leave no trace, cause no harm, and initiate no chemical change. Their presence is a silent, cosmic rain. This reality invites a deeply personal and reflective question. Does the knowledge that our existence is a delicate byproduct of a vast, invisible framework make our lives feel more precious or more incidental? Are we a rare and beautiful flowering in a cosmos dominated by darkness, or simply a fleeting pattern in a grand design that is largely unconcerned with our presence? The answer may lie in the realization that our ability to ask the question, to map the invisible, is itself a remarkable consequence of the very cosmic processes we seek to understand. The universe is held together by a ghost. This invisible substance, dark matter, is the cosmic architect whose gravity orchestrates the motion of galaxies, bends the fabric of space, and provides the essential scaffold for all of existence. We have journeyed from the unexpected speed of stars at the edges of galaxies, a mystery first illuminated by Vera Rubin, to the warped light of gravitational lensing that maps unseen mass. We have listened to the ancient whisper of the cosmic microwave background, a fossilized blueprint that confirms dark matter's dominant role from the very beginning. The evidence is overwhelming and consistent, pointing to a simple, staggering fact. The stuff of stars, planets, and life itself makes up less than 5% of the cosmos. The rest is a darkness we are only learning to see. This hidden component is not a minor detail, it is the foundation. Without its gravitational pull, the primordial gas of the early universe would never have gathered together. There would be no galaxies, no stars, and no planets. The majestic cosmic web, with its glittering clusters and vast, empty voids, is a direct imprint of dark matter's invisible structure. Our entire visible universe is a delicate embroidery on a dark fabric we are just beginning to trace. The hunt to identify this substance has pushed science to its limits. We have searched for heavy WIMP deep underground and scanned the skies for the gamma-ray glow of their transformation. We have tuned resonant cavities to hear the collective hum of ultralight actions, and even considered the possibility that dark matter is a sea of ancient black holes. Yet, for all our ingenuity, it remains elusive, its true nature a secret the cosmos guards closely. This is not a story of failure, but one of profound mystery. The unresolved puzzles, from the missing satellite galaxies to the unexpected cores of dwarf galaxies, are not flaws in the theory but guideposts, pointing us toward a deeper truth we have not yet grasped. They remind us that our understanding of physics is incomplete. The implications ripple across every domain of knowledge, from cosmology and the fate of the universe to the fundamental laws of particle physics. Ongoing research across countless fronts, from the Vera C, Rubin Observatory's relentless sky survey to the ultra-sensitive detectors placed deep underground, continues the pursuit. This collaborative, global effort is more than a technical challenge. It is a fundamental expression of human curiosity. We are trying to understand the hidden framework of our reality. As we stand on the brink of new insights, with powerful new tools and a clearer map of the invisible than ever before, we are forced to reflect. What will we learn about our own place in a cosmos where we are the rare, visible exception, living in a universe dominated by darkness? This invisible puppeteer, whose influence we have traced across the cosmos, remains one of science's greatest enigmas. The evidence for its existence is a symphony of clues, from the swift dance of stars to the warped light of distant galaxies, all playing in perfect harmony to announce a profound truth. We live in a universe shaped by a presence we cannot see, yet, for all we have mapped its gravitational shadow, its fundamental nature slips through our grasp, a quiet force in the cosmic machine that continues to drive innovation in our deepest laboratories and our most ambitious telescopes. This quest compels us to build more sensitive detectors and to write more elegant theories, pushing the very boundaries of human ingenuity. A leading cosmologist once reflected that this mystery teaches us a deep humility. It reminds us that reality is far richer and stranger than our limited senses can perceive, and that the universe holds magnificent secrets waiting just beyond the light. This journey does not end here. Every new observation, every data point from a new sky survey, brings us closer to a revelation that could rewrite our understanding of physics itself. I encourage you to carry this curiosity forward. Follow the announcements from observatories and research teams, for a breakthrough could be just around the corner. Share this video with someone who looks up at the night sky and wonders what is really out there. And in the comments below, tell me what aspect of this cosmic mystery captivates you the most. Is it the search for the particle itself, its role as the great cosmic architect, or the philosophical questions it raises about the nature of reality? Your engagement fuels this shared exploration. For more deep dives into the wonders of space, be sure to subscribe. The universe is full of mysteries, and together we can continue to bring them into the light.